What I like about this project is that it is a very good example that shows how quantity yields a new quality. With that I mean that after many years of research by the scientific community on 2D materials, it was now us who were fortunate enough to make this milestone discovery of a new 2D material which will have semiconducting properties.
Nowadays, electronics are a big deal, right? We have the phones, TVs, tablets, but they're limited in the fact that they're very rigid, right? Because they are all based on a material called silicone, which is great, but it's very brittle, right? You give it a little bit of pressure and it cracks and it breaks. What we're trying to do now is move from silicon-based things to organics. There are a lot of pros to using organics, but a cool thing is that you kind of break this dependency on having to have something rigid, like a tablet or a phone, where you now move from electronics being rigid and straight to being able to be flexible and bendable. So you can do anything from having TVs that you pull down, like that are wallpapers that you can put up and pull down like a piece of paper. You can have things like wearables, like watches or bracelets that can wrap around and can have electronics all throughout the entire thing. So you gain a lot of flexibility, literally, from moving from traditional silicon-based computing to organics. There's a really famous material that was made a while ago, got a Nobel Prize, got a lot of attention in the field, and that was graphene. And so this is a single layer of just carbon atoms, that's all it is, and it's a really good conductor. So like copper, it conducts electricity really easily. And then there have been other materials being made, another famous one being nanomesh. It's made out of boron and nitrogen, and that one does not conduct electricity very well.
So in graphene, it is a good conductor, but you cannot control the current. So once the current flows, you cannot switch it on and off whenever you want. With the boron nitride, it's an insulator. You need very high voltage or a lot of energy to use it in devices, which is not good from efficiency point of view.
So something like copper, you can flow electricity through it really easily. That's why wire is made out of it. And then something like rubber or wood, electricity doesn't flow very well through it at all. So on one end we have graphene, which is like copper, conducts really well. And on the other end we have nanomesh, which is boron nitride, and that conducts really poorly like rubber. So we have these two main 2D materials. So that's cool that we have the both ends of the extreme, but we're missing a really important kind of middle ground, and that is a semiconductor. So it's a little bit of both. It can conduct electricity sometimes and sometimes not the other, and that depends what you do to it. Kind of the basis for almost all computing. Silicone, so your phones, your computers, they all run on semiconductors. So this material is extremely important, and so therefore it's a very obvious absence in 2D materials. We set out to kind of remedy this and introduce a 2D material. So we weren't the first to notice this absence of a semiconducting 2D nanomaterial. So many people have been trying to make this, and kind of the most obvious way to make it, if we talked about two previous materials before, which is graphene, which is all C, and the nanomesh, which is all B and N's, is to simply mix them together. Mix your B's, your N's, and your C's all together, and then hopefully you'll get kind of a Goldilocks effect where you get something in the middle, not all the way non-conducting, not all the way conducting. They were all really cool experiments. They got cool things out of it, but none of them truly made a 2D kind of perfectly patterned, nicely made material. We kind of teamed up with some theorists and some chemists to kind of try to make this ideal small puzzle piece or Lego piece. And the idea is that if you could throw this on a surface, that these pieces would connect in perfectly different ways and they would snap together to make a bigger picture of 2D materials. So we were making small building blocks, small little Lego pieces that would snap together in unique sites and then make kind of perfectly uniform two-dimensional material that would have B, C's, and N's in it, and in certain positions because we fabricated them to be that way.
So for that we use metal substrate. In this case we use high purity iridium or rhodium crystal. In order to link these molecules together we need heat as a driving force or energy as a driving force. So we heat our substrate to close to 1000 degrees Celsius temperature. We shoot these molecules in the vapor form onto the surface of that metal.
So now we made a material, but we need a way to kind of prove and see that it exists.
So if you want to look at the atomic structure of a material, you need something which has a resolution where you can see individual atoms and you can see how they are arranged in a particular structure. So scanning tunneling microscopy is the technique which can provide you such a resolution. So for example, with an optical microscope, you have a resolution where you can see details of a cell. But if you want to go beyond that, you have to use something different.
We use a technique called scanning tunneling microscopy. We are able, using this, to actually visually see atomically small structures.
So in this technique, we take a metal wire which is very sharp. When we bring it close to our material and we apply a very small voltage between the material and the tip, so it gives enough energy to the system so that the electrons from the material, they jump between the material and the tip. And by moving the tip over the material, we can map how many electrons are traveling between the material and the tip. So using that map, we can actually create a real image to see how these atoms, which are boron, carbon, and nitrogen, how they are arranged in a pattern.
We believe that this discovery will stimulate lots of follow-up research activity by our colleagues, by the scientific community, and all that will help establish that material as a candidate for new electronics applications that might be thinner, more flexible, and more energy efficient. I'm Axel Enders, the fearless leader of this project. I'm adjunct professor at the University of Nebraska in Lincoln, and I'm also a full professor at the University of Bayreuth in Germany.
I'm postdoc at University of Nebraska, Lincoln. I've been working on this project for 3 years.
My name is Paulo Costa. I'm a graduate student at UNL. I've been on this project for 3 years.
Now that's nano.